Welcome back, students. This is the session 5 from the playlist of oscillations. The topic is forces and energy in simple harmonic motion. And today I have written down here one bullet point to start with. So, in this point, I have basically tried to derive the equation for the time period in case of an object which is executing the simple harmonic motion. So we know that in the case of a simple harmonic motion, a restoring force acts on an object when it is displaced from its mean position. So the restoring force is equal to minus kx, where x is the displacement and k is the force constant, and the force is also equal to mass into acceleration. And in the case of the an object which is executing the simple harmonic motion, the acceleration is equal to minus omega square x, where x is the displacement and omega is the angular velocity. So from this equation we can here see that this f is equal to ma minus m omega square x, and this is equal to minus kx. So from this equation, that is minus m omega square x is equal to minus kx, I am getting the value of this omega square, which is called the angular velocity, or it is also termed as angular frequency. So angular velocity or the angular frequency, this is equal to k by m, or we can say that the angular velocity or the angular frequency, this is equal to under root k by m. Now we know that the time period is equal to 2 pi upon omega, or omega is equal to 2 pi upon t. So this is equal to 2 pi into under root m by k, because omega is equal to under root k by m. So this is how we find the time period of an object or a particle which is executing the simple harmonic motion. Now the next point here is, we will try to find the total energy of a particle or a body which is executing the simple harmonic motion. So a particle or a body which is executing the simple harmonic motion will have two types of energies, that is the total energy will be equal to the sum of kinetic energy and the potential energy. Now the kinetic energy of a particle which is executing simple harmonic motion can be given by half m v square, where v is the velocity of that particle, and we know that in the case of a simple harmonic motion, v is equal to omega under root a square minus x square. I have already derived this equation in one of my sessions from this playlist of oscillations, so you can access, I think that is the session number 2, and so you can just go through that playlist or through that session, and you can just know that how this velocity of a particle which is executing the simple harmonic motion is derived. So v is equal to omega under root a square minus x square, where a is the amplitude of the simple harmonic motion and x is the displacement. So if I put this value in this equation, I will be getting the kinetic energy as this v square will be equal to omega square and in bracket a square minus x square. So this is the kinetic energy of the particle or the body which is executing the simple harmonic motion. So this is the kinetic energy, and this I am writing it here on the left hand side of this board, which is equal to half m omega square and in bracket a square minus x square. Now we have to find the potential energy of this particle which is executing the simple harmonic motion. So in order to find the potential energy, we have to first of all find the work done by the restoring force. So the work done by the restoring force will be given by f dx, where dx is a small displacement of that particle from its mean position. And so if I integrate this equation from that is dw, this can be integrated from 0 to x, where x is the displacement of this particle. And so if I integrate this equation, I will be getting as this: w is equal to now f is equal to minus kx, and so here since k is a constant, so minus k will be taken out, and I will be getting the value as x square upon 2. So the work done by the restoring force is equal to minus 1 by 2 kx square. Now since the potential energy is equal to the negative of work done, the potential energy is equal to the negative of work done. So the potential energy of the particle which is executing the simple harmonic motion, this would be equal to half k x square. So this I am writing it here now. So this is equal to half k x square. So the total energy of the particle which is executing the simple harmonic motion can be written as 1 by 2 m omega square a square minus x square plus 1 by 2 k x square. Now we know that omega square is equal to under root k by m. So we can say that, omega is equal to under root k by m. So k is equal to omega square m. So I will be putting this value here. So the total energy will be equal to half m omega square, I am opening this bracket, minus half m omega square x square plus half. Now I will be putting the value of k as omega square m. So that will be equal to m omega square x square. So this value gets cancelled out. So the total energy of a particle executing simple harmonic motion is equal to half m omega square a square. So a particle which is executing the simple harmonic motion has got the total energy equal to half m omega square a square, where a is the amplitude of this simple harmonic motion. The time period of the simple harmonic motion, which is equal to 2 pi upon omega, this is equal to 2 pi under root m upon k. This is the value which we have just now derived, just few minutes back. Now, third important thing, in the case of a simple harmonic motion, the restoring force is equal to minus kx, and this is equal to minus, this is equal to m into a, and this is equal to minus m omega square x, because the acceleration of the particle executing simple harmonic motion is equal to minus omega square x. So from here we were able to find the value of omega, which was equal to under root k by m, and omega is the angular frequency, or you can also term it as angular velocity. So we have found the angular frequency or the angular velocity. We have also found the time period. We have also found the total energy of the particle executing simple harmonic motion. And so here this formula, that is f is equal to minus kx, which is equal to minus m omega square x, needs to be remembered by all of you. Okay. So this is all I have for in this today's session. That is, I just wanted to discuss about the total energy of the particle which is executing simple harmonic motion, and I also wanted to derive the time period of the particle which is executing simple harmonic motion. Apart from that, there is one more important formula, that is the velocity of the particle which is executing simple harmonic motion. This is also equal to omega under root a square minus x square. This also needs to be remembered by all of you. And the acceleration of the particle which is executing simple harmonic motion, this is equal to omega minus omega square x. So thank you very much for joining this session. In the next session, we will be doing a couple of numerical problems based on this topic, that is forces and energy in the simple harmonic motion. So till then, have a nice day. Bye.